Uh, you are all welcome. You're welcome to the section. Uh, Hello. Oh, I hope you can all hear me clearly. You're welcome to the section. For this week, we'll be looking at surface tension. Today, we'll be dwelling on theory mostly. And then by the next time we meet, we will dwell mostly on calculations. You're all welcome. Uh, the surface of a liquid behaves as if it's an elastic body, like a stretched membrane. The strength of the membrane depends on the I'm having some connectivity issues here. Please pardon me. The strength of the membrane depends on the nature of the liquid. Now, for example, like if you have soapy water or ordinary water, the surface tension will differ from these two kinds of water. Now, surface tension, uh, this phenomenon of surface tension makes a liquid behave in a spherical form. Spherical form. For instance, now, if children are blowing soap bubble, you create soap bubble, you see it form a sphere, circle-like uh, substance floating in the air. So why not some other kind of shape, like it being in a table-like form or in a square-like form? The the answer to that is because of the impact of surface tension. The impact of surface tension. So this phenomenon, as we have here, this phenomenon can be observed in nearly spherical shape of small drops of liquids and of soap samples. This it now, apart from the fact that some things can float in water, you can observe an insect standing on water. Not that it was submerged. Here, I'm trying to differentiate from this Archimedes principle, where an object flows on water as against being on water, like standing on water, standing on water. So we can see that sometimes you can have a pin be on water, no part sinks, where you have some parts up, some part down, as against the principle of Archimedes. And here we, so what is supporting that uh, pin, or what makes an insect easily stand on the surface of the water and not go in a lightweight, this the substances I'm making example of are lightweight, so they can stand underwater. The emphasis I'm making here is to let us know that the weight of the substance or insect or object on the surface of the water is not greater than the surface tension. Else, some parts we could be talking about the Archimedes principle. Now, we also have a situation where a razor blade can be supported by the surface tension of water. The razor blade is not floating. If pushed through the surface, it sinks through the water. So, yeah, the part considered here, or the focus here, is to let us know that it's not that the pin per se was able to displace some amount of water equal to its weight. No, that's not the case. Okay, it doesn't. It is not that that's a flattened. It doesn't cover enough space to be able to displace as much water equal to its weight, so as to float. But so in a situation that if the pin or the razor blade is pushed down, it gets to the bottom of the water. Uh, Surface tension accounts for the spherical shape of liquid drops, e.g., if you have raindrops. I'm not saying when the rain is heavy. That's not what. Let's say on the roof, let's say it's dripping, you have it dripping, it was falling on you, it comes out in a spherical shape. In a spherical shape, we, we have oil drops. So we are talking about drops now, not a whole volume, or not much volume floating, but just drops. So let's say you have oil that has finished from the bottle or the container, and you still want to get the list out. Or let's say we're drinking uh, some liquid substance, and you want to get the list out, the drop out. You are going to see that it behaves as if is a kind of like a spherical shape, where the it's going to have a sharp tip. It's going to have a sharp tip, and then it bulges out from the sharp tip, bulges out. So that shape, that spherical shape, is due to the surface tension. Is due to the surface tension that has brought on such a shape. The We can have polydrops of molten metals. Okay, let's say we heat up a metal to some kind of high uh, temperature, such that it was uh, in a liquid form. That is, has changed state. That's changed state. It is going to behave as if it's a drop. We are going to have that shape. That shape, spherical in nature. This is as a result of surface tension. The causes of surface tension. Now, that is what we want to look at. Causes of surface tension. Now, there is what we call this attraction between molecules in a liquid. If you were to consider this figure here, now let's look at the two molecules at the middle part. The two molecules at the middle part has equal forces of attraction spread out across all the regions. It is evenly distributed. So it's going to behave in a normal way. However, the molecules at the surface, these two molecules at the surface, they don't have equal for, magnitude of attraction outside the region, sorry, outside the space, because there's no other molecules there. So the net attraction that the molecules at the boundaries will witness will be directed inwards. It's be directed inwards. The force of attraction there, the force of attraction will be directed inwards. And so that is why at the edge, since there are no other molecules attracting them equally, the edge will now become a form of elastic. It will be Steven, as most of the forces are pulled inside. So the cause of surface tension is mostly attributed to the attraction of molecules between each other, attracting each other, where so that the net attraction is towards the inside, because there are no other similar molecules outside the region to give the molecules at the edge same kind of attraction, or same kind of pull, same kind of pull. And so that is the main cause of surface tension. I'll read this out. Due to the cohesive forces, a molecule is pulled equally in every direction by neighboring liquid molecules, resulting in a net force of zero. The molecules at the surface do not have the same molecules on all sides of them, and therefore are pulled inward. This creates some internal pressure and forces liquid surfaces to contract to the minimum area. There is also a surface, a tension, I beg your pardon, let me take that again. There is also a tension parallel to the surface at the liquid air interface, which will resist an external force due to the cohesive nature of water molecules. I don't know if you have done what we call continuity. Continuity, that is assuming that, or Archimedes, or this flow, water flow, the Bernoulli's principle that I wanted to talk about. Now, once you send water through a pipe and the water is about to flow out, there will be some forces at the other end trying to push the water backward. So these forces is against the flow, the direction of the flow of the liquid you are sending through the tube. It will be forced backward. So that same forces now will be at the edge of the. I'm trying to bring that analogy to the edge. The edge. They will at the interface of that liquid. There is a kind of an external force pushing against the expansion of that water. You know, we say, I don't know if you have done Newton's third law, that for every action there's equal and opposite reaction. So at the surface there will be some negative forces going in the opposite direction, the negative forces going in the opposite direction. So that negative force that goes at the opposite direction ensures that the substance behaves in a stretched form, a stretched membrane or a covering. So the neighboring force molecules will attract each other and maintain themselves within the range which they attract each other. Outside that range, which they have net attraction, they will form a kind of covering. They will house themselves inside a given region. Uh, I hope that is all right. So the surface tension definition, the property of a surface of a liquid that allows it to resist an external force due to the cohesive nature of its molecules. Okay, we have explained here that surface tension depends mainly on the force of attraction between the particles that are within the given liquid. This principle also holds for gases as well, for solids as well, but that of liquid is more pronounced. That of liquid. So surface tension is defined as force over unit area. Force over unit area. Now the unit is Newton per meter squared. If this were to be a life class, that is a physical class, I mean to say, I would have asked us to get out the dimensions of surface tension, just to play around with it. That is, you should be able to do that easily. Okay, if you don't know, you should be able to resolve that. You write the equation out, and then you get out your dimension. The dimension of this is the unit. The unit is Newton uh, per, per meter, Newton per meter, which is obtained from the formula force divided by unit length. There are two forces of attraction for a liquid in a container. Two forces, we have two forces. One of them is cohesive force, and the other is adhesive force. Now, the cohesive forces occur between molecules of the same type. Molecules of the same type. There's this attraction between molecules of the same type. For instance, between liquid and liquid water, the molecules of the water will attract each other. Or liquids can, for example, be held in a open container because cohesive forces hold the molecules together. Okay, and then the other force, adhesive. Okay, one should be able to easily remember this: cohesive, together, cohese, to cohese, to togetherness, and adhesive. That is, you are adding, kind of an addition. So, adhesive forces occur between molecules of different types. Such example could be where we have liquid drops clinched to the window panels. So that is so. Most of the things we'll be looking at will be to evaluate these forces. Sometimes they play together. That is the interplay. You can have it. Uh, Take for instance now, I just mentioned liquid drops that clinch to window panels. You can have that in circular form now clinching to a window panel. So what am I trying to point out here is that that uh, water drop will have two forces, these two forces occurring concurrently. One, the cohesive force between the internal molecules, and the other force will be that the molecules at the boundary will now attract itself to another kind of molecule. A very good example of this is that where you could have maybe water on the wall. some kind of liquid drops on the wall or on the paint. You have paint on the wall. The question is, why didn't they just drip down? You have it being wet there. You can just see. Sometimes you have this situation. So it arises because there is also some attraction between the molecules and the wall or the paint on the wall. So that is the adhesive forces that occur. The next thing we want to look at is angle of contact. Now, when these forces come to there's this interplay, there is what we call the angle. There's the meniscus. There's a meniscus. It could be something on the top or something at the bottom. Some can be curvy. Some can be in a cave-like nature. Here we say the angle between the meniscus and the containing walls of a column of liquid measured from the vertical wall between the surface of the liquid to the position of the tangent to the meniscus at a point of contact with the wall. That is the angle of contact. Here, if you were to extend this, the angle of contact, you can see that angle of contact that it makes between the meniscus and the wall. The angle here we measure, this other angle here we measure. When cohesive forces are greater than adhesive forces, the contact angle theta lies between 0 and 90. Okay. When cohesive forces are greater than force, I beg your pardon, when cohesive forces are greater than cohesive forces, the angle theta lies between 0 and 90. When cohesive forces are smaller, in this case, when it is smaller, when cohesive forces are smaller than adhesive forces, being smaller than cohesive forces, the angle lies between 90 and 120. So in the first case here, where we have this angle, where this first instance here is where the angle is between 0 and 90, and here the adhesive forces are greater than cohesive forces. That's the first instance. In this other instance here, the contact angle, if when measured, we have here that the cohesive forces are smaller, much more smaller compared to the cohesive forces. The adhesive forces much more smaller compared to the cohesive forces. Then the contact angle lies between 90 and 180, is greater than 90, but less than 120, not flattened. For a liquid standing in a container, a meniscus forms. It can be convex or concave. Like I said, it can bulge out or cave in, can come out or cave in. So that, but it is an interplay between the adhesive forces and the cohesive forces, which I say that both occurs at the same instance. They occur at the same instance. For a concave meniscus indicated that the molecules of the liquid have a stronger attraction to the material of the container. Okay, that is adhesion than to each other. A convex molecules indicates the molecules have a stronger attraction to each other than to the material of the container. So The first case is the aeration case. The second case, the B part is the convex meniscus case. We move on to capillary. Capillary is the tendency of liquid to rise or be suppressed in a narrow tube. The narrow tube, we call that narrow tube capillary tube. So, for instance, now when you use your straw, if you insert your straw inside your drink, you may maybe just see it rising up in that straw. So that straw that you are using to take the drink is regarded as a capillary tube. The capillary action is the rise or fall of liquid when it is in the narrow tube or when it is in a capillary tube. The action effect depends on the relative strength of the cohesive and adhesive forces. Like we have been saying here, this two, of course, if theta is less than 90, then the liquid will be raised. If theta is greater than 90, it will be suppressed. Mercury, for example, has its large surface tension and a large contact angle with glass. When we are trying to compare the normal liquid with mercury. So for the normal liquid now, or let's say normal liquid, I mean water in this case. Water, while I said normal, because your drinks too, this 7-Up we take can also be normal liquid. That's what I'm trying to say. Water, when we have that, we put that, we see that it will rise, but the meniscus will sort of cave in. However, for mercury, if we put in a capillary tube, the rise will suppress. It will be lower than the standard height, the height of the remaining part. And in this case, the meniscus will be will budge out. We'll have the B part of that incident. Okay, mercury suppressed in a glass tube because its contact angle is greater than 90. Surface tension exerts a downward force as it flattens the mercury, suppressing it in the liquid. The, uh, the dash line, we'll get to the, don't worry, we'll get to the figure so that we'll see what we are discussing. The surface tension, the dash line shows the shape the mercury surface would have without the flattening effect of the surface tension. The B part water, okay, this is the case. This is the case here. I'm trying to talk about in the in this one. The first case here is the water. The first case here, this is the water situation that if you note it rises, but the meniscus here is submerged. Is curved in, while here but the mercury budges out. It budges out and trying to run away from concave and convex uh, mentioning, because that could be confusing to some of us if we have not done any, if we have not reminded ourselves about lenses or those kind of the lenses and shapes. So at running away from such mentioning of concave and convex surfaces. Now, there is a formula to calculate the height. It either rises or falls. The height it rises or falls. So the height here, if we have this surface. Let me enlarge it. We have the height. The height here is given as h. That is the rise in the tube, in the capillary tube, is given as h. The surface tension as the gamma. The gamma is at the surface tension. Rho here is the density of the liquid, and the radius r, while g is acceleration due to gravity. So we have this here. So the equation for evaluating the height, this can be derived, but we are not in for that. The expression for evaluating the rise or fall, otherwise, of the height in the capillary tube is giving us h equals to 2 times gamma times cos theta. That is the angle it makes, the angle of contact, as we can see here, divided by the density of the liquid times the acceleration due to gravity times the radius of the capillary tube. We want to consider wetting. Wetting is the ability of liquid to form interface with solid surfaces. That is where we say wetting occurs. We are looking at the ability of a liquid to form an interface with a solid surface. In this case, the contact angle between the solid and the liquid is a measure of the degree of wetting. The angle of contact, or the contact angle between the liquid and this solid surface, is a measure of the degree of wetting. A smaller contact angle, and the smaller the contact angle and the smaller the surface tension, results in a great degree of wetting. As we see here. Now, in this case, now the contact angle here is much small. The contact angle is like 0 degrees. We cannot measure out anything from here. The spreading, the contact angle is 0, and so the wetting is large. You can see it's spreading out when the contact angle is 0. There is a spreading, and then when the contact angle is less than 90, we see the wetting. It forms more like an arc. We have an arc there, or can we call it a half circle? The arc would not be greater than the half circle. Now, that is the wetting. Now, the wetting section, we have that the angle of contact is greater than 90 degrees. If we were to take the angle of contact this way, greater than 90 degrees. That is, in this case now, we are having something to a whole circle or something almost a circle, but is a region of around 3/4, 3/4 of a circle, where the contact angle is greater than 90 degrees, where we describe such as the dewetting process. Soap bubbles, we want to look at the pressure that the soap bubble has. When we have this, uh, let's say you blow the soap bubble in the air and it forms droplets, there's this inward surface tension that forces bubbles to be approximately spherical and raises the pressure of the gas trapped inside relative to the atmospheric pressure outside. Okay, we're talking about some equal forces balancing. When we say a force has to balance, the force has to balance. Where we have a situation of uh, the act of forces being equal and opposite. When you have a bubble, there will be some pressure inside working as against to expand the bubble, and there will be under pressure outside that is working to keep the bubble in place. Just like when you have when you have a balloon in the air, the balloon in the air inside, when you will be exerting a pressure on the wall to expand it more, whereas there will be another pressure due to the atmosphere that will be forcing the balloon to go down, to go down. And so sometimes sometimes when you can have a balloon bursting, or this Christmas balloon, just based of sound, wow, it comes out, because at a certain point the pressure inside was always working to expand, whereas that of the outside was always trying to keep it up. So any opening, if the body or the membrane of the balloon cannot hold it, that's where we have that sound. Now the pressure there, the pressure inside the balloon, actually, or let's call it that of the, in this case, that of the uh, soap bubble, is giving us P equals to 4 times gamma over R, where we are already very familiar with our gamma, which is the surface tension. So bubbles have two surfaces, the inner and the outer surface of the bubble. The first form surface tension is F equals to 2 times surface. The F is 2 times the surface tension, gamma times the length, unit length. So the bubble can also be a spherical volume of gas inside a liquid. In this case, the pressure is P equals to 2 times the surface tension divided by R. So it varies in some surfaces or some kind of droplets. You have this, the first case for a spherical bubble, but for a gas, for that of a gas, for the gas now is giving us 2 times gamma divided by R. All right, we are having examples to resolve. I would have ask us to pick up our pen and barrels to solve one or two problems. Number one, calculate the gauge pressure inside a soap bubble 2 times 10 to the power minus 4 meter in radius using the surface tension for soap water as y equals 0.0370. This is a straightforward situation where we have using that P equals to 4 gamma over R. We insert the gamma divided by the radius, and we have that the pressure or the gauge pressure of the soap bubble is 740 Newton per meters square. There's another situation, an example here. We want to calculate the radius where we are given the radius of a contact in a situation where, in a capillary situation, where we have a rise or a fall, and we have been given some interesting parameters to evaluate. Okay, now where we have this, the angle is given, the height is given as 100 meter. This is the gamma, and this is the density of water, or can we say soap water. The angle is given cos theta. The angle is given as 0, and the surface tension as everything well spelled out there. We can always evaluate when given this kind of situation. If it were to be a live class now, I would have called out some questions for us to resolve, not what we are seeing there. I like to play around, because when you can solve some of these things, it gives you confidence that you can always resolve it in the exam. You are already used to these problems. I would advise that we solve as many problems as possible from different different textbooks. Get your hands busy, solve a lot of problems, because in the exams you will be faced with so much of it that what I mean is that it may be some things that are unexpected that you meet. So once you have solved as many as possible, you will be safe. You'll be sure of yourself. So I will advise that please get as many problems as possible and then solve. Another problem here is we want to determine the surface tension, or the tension, the force, and we are given a capillary tube of 0.05 centimeter, but stands vertically in a wide vessel containing a liquid or surface tension 30 dm per cm. A liquid wets the tube and has a specific gravity 0.8. Calculate the rise of the liquid in the tube. Calculate the rise of the liquid in the tube. And there we have this. This we are expected to take the contact as sorry about this. This shouldn't be the I think there's no need starting with the first equation. That's what I'm saying. There's no need for us to start with the first equation. Just that if you use this equation, the height we are calculating, you insert everything we are given, and then you come to 0.33 meters. It's very straightforward. It's very straightforward to see. Uh, another problem, another problem. These are just how we can calculate from one. We can just play around with that equation. So I would like to just go through. You have this material, so there's no need us going through but like, everything here. While we're also looking at this kind of exercise, uh, if you are to try this at home, just sit down. Let's look at this exercise. Let's forget about the calculations for now because they are straightforward. They are being solved here. Okay. Take for instance, this other one, we were looking at the age. We're trying to determine the height. This is the expression we use. 2 times the force, sorry, the gamma surface tension, 2 times surface tension across theta divided by rho